Welcome. Let's look at a brief introduction to the cross product. Now, before we get into the mechanics of the cross product, there's a few things that we should know. First of all, the cross product is only one method for multiplying vectors, and it is also known as the vector product because the result of a cross product, the result of that multiplication process, produces a vector. And lastly, that a cross product is only defined in 3 dimensions, so only defined for vectors in R3. Now, interestingly enough, the cross product does have a physical representation, if you will, and that's known as the right-hand rule. So if you were to take a right hand and you were to point your index finger or your first finger in the direction of the first vector in the cross product, and you were to take your middle finger and point it in the direction of the second vector in the cross product, pointing your thumb outwards would indicate the direction of that cross product vector. This process is known as the right-hand rule, as it works with the right hand, not the left. The cross product also has a geometric interpretation. If you were to take the cross product of 2 vectors, let's say A and B, and then find the magnitude of that vector, then that magnitude would be the same as the area of a parallelogram built out of the 2 vectors A and B. So this parallelogram we have here, its area is the magnitude of vector A cross vector B. Now, we can say that that magnitude of vector A cross vector B is the same as the magnitude of vector A times the magnitude of vector B times the sine of the angle theta, that is the angle of separation between angle A and B. One important note, though, we always consider that angle theta to lie between 0 and 180 degrees or 0 and pi radians. So that's an important consideration when you're considering this geometric relationship related to the cross product. Now, the cross product can be found algebraically, and it is based on using determinants of matrices. So let's go ahead and take a look. So what we'll do is we'll set up a 3 by 3 determinant. So let's think about finding the cross product of the vector 2, -1, 4 and the vector 3, 2, 5. So we set up our determinant and notice that in the first row of the matrix, we put the unit vectors I, J, and K in the first, second, and third columns. Next goes the first vector of the cross product. So in the next row should go the vector 2, -1, 4, and we see that here. And then in the third row, the last row should be the second vector of the cross product. That's the 3, 2, 5. And once we have this determinant set up, we expand it. And the way we expand it is we start with the first column, the vector I. We eliminate the row and column in which I occurs, and we do the subdeterminant. So we do the determinant of -1, 4, 2, 5. And that's what we see here. Then we move to the second entry of the first row, and we remove that row and that column, and we do the subdeterminant of what remains. So in this case, 2, 4, 3, 5. Now, when we move to the second entry, the J entry, it's important to remember that there's a minus sign here. And this minus sign is derived from how we find determinants of 3 by 3 matrices. Now, having taken care of the second entry of the first row, we now move on to the third entry of that first row. And so what we have is the unit vector k, and we remove the row and column that contain k, and we end up with this subdeterminant that's a 2, -1, 3, 2. And so that gives us the third part of our cross product. Notice that because we still have unit vectors I, j, and k, we are creating a new vector. The x component being the scalar that is the result of that 2 by 2 determinant being multiplied by I. The y component, or the j component, will be the opposite of the determinant of that little 2 by 2 matrix that's multiplying the j vector. And similarly, the z component, or the k component of our cross product vector, is going to be that scalar multiple that's represented by that little 2 by 2 matrix multiplying k. So if I were to compute those various determinants, starting with the 2 by 2 multiplying vector I would multiply the diagonals, so I would have entries, so I'd have -1 times 5, and then I would subtract the product of the off diagonal entry, so the product of the 2 and the 4. And so I'd have -5 minus 8, and so -5 minus 8 will give me -13 times the unit vector I. Then we move on to our second 2 by 2 determinant. Again, we multiply the diagonal entries of a 2 by 2. So I'm going to have 2 times 5. And then I subtract the product of the off diagonal entry. So that would be -3 times 4. So that would be 10 minus 12. 10 minus 12 is a -2. But recall, with the j component, we have this negative we have to account for, so that becomes +2j. And lastly, we look at the k component, or the z component. Again, little 2 by 2 determinant, we multiply the diagonal entries, so that's 2 times 2. We subtract the product of the off diagonal entries, that's a 3 times a -1. So we have a 4 minus a -3. Well, 4 minus a -3 would give us a +7. So the cross product is going to be -3 to 7. So now we want to look at torque as an application of the cross product. And if we look at this diagram here, we have a bolt of some type with a wrench where R is the length of the wrench, or the lever arm, in this particular context. You're most likely familiar with either trying to tighten or loosen a bolt. And so the force is typically applied here at the end of the wrench. So that's why the force arrow is indicated there. Torque is a rotational force that helps to either loosen or tighten things like bolts. So notice that in this diagram, to help us make sense of why the cross product is useful, we've translated this force vector from the end of the wrench to the bolt where the center of rotation is. So while technically the force is applied here at the end of the wrench or the lever arm, it makes sense to make sense of a cross product. We're going to consider it being located here at the bolt or the center of the rotation. So with that in mind, thinking about the right hand rule for cross products, if I, with my right hand, had a right hand threaded bolt, then this radius R cross product with this vector, force vector F, would produce an upward vector R cross F. Take a moment and try that yourself. Have your index finger pointing in the direction of R, your middle finger in the direction of F, and if your thumb is perpendicular, it shows you the direction of the cross product. So it is an upward pointing vector. So basically then this represents the rotational force or the torque. Now, one thing to note, the typical symbol for torque is this lowercase Greek letter tau. Now, depending on the threading of that bolt, that torque, that rotational force, will either loosen the bolt or tighten the bolt. So now let's apply that reasoning here on this particular bolt and wrench. We've got a situation where we have a bolt, and a bolt is being tightened by applying a force of 6 newtons to a 0.15 meter wrench. The angle between the wrench and the force vector is 40 degrees. We want to find the magnitude of the torque about the center of the bolt. So we're trying to find the magnitude of the torque around that point. I'm just going to label that C for center. So we can see that this force is being applied here on the end of the wrench. And that's not where the center of rotation is. So what we're going to do is we're going to translate that to the center of the wrench. So we're going to consider our force vector to look something like this. Now, notice that the two force vectors are parallel, and the wrench then becomes a transverse through the two parallels. So with this translated force vector, then I know that we also have an angle of 40 degrees between our lever arm and our force vector. So we're asked to find some information about the torque. So torque, or the Greek letter tau, is going to be our radius lever arm cross product with our force vector. Now notice that we're actually asked about the magnitude of that torque. So that's going to be the magnitude of torque is equal to the magnitude of the radius vector cross product the force vector. Now recall that we have this geometric relationship, so the magnitude of a cross product is the product of the magnitudes of the two individual vectors times the sine of the angle between them. So in this case, that's going to equal the magnitude of the radius vector, or the lever arm, times the magnitude of the force vector, times the sine of the angle of separation, or the angle between the two vectors. Now going back to our problem statement, we're applying a force of 6 newtons. Notice that that's not given to us in a component form. So we can determine from that that this is actually the magnitude of the force. So we know that the magnitude of the force is 6 newtons. We also know that the length of the wrench is 0.15 meters. So that is the magnitude of the lever arm, or the magnitude of R is 0.15. So we can use those two pieces of information. The magnitude of our lever arm, or the length of the lever arm, is 0.15. The magnitude of the force, or the total force being applied to the wrench, is 6 newtons. And then we have the sine of the angle between them. That's a sine of 40 degrees. Now notice that our lever arm, or the length of that wrench, is in meters, and our total force that is applied to the wrench is in newtons. So this will have units of Newton meters. Now, sine of 40 degrees is not a simple value to determine. So let's go ahead and approximate this. And if I were to approximate this, we would end up with approximately 0.5785 Newton meters. I hope you find this helpful.